Hello, my name is Mitchell Hunt. This is my presentation on horizontal stabilizers for advanced materials with aerospace applications. The stabilizers are located at the tail end of the aircraft. The horizontal stabilizers extend to both the left and the right sides of the aircraft and support the elevators. The role of the stabilizers of an aircraft, the horizontal stabilizers that is to control the pitch of the aircraft. In the resting state, the horizontal stabilizers are supposed to provide both dynamic and static stability of the aircraft. Otherwise, when the aircraft is flying, if any sort of dynamic force pushes the tip of the aircraft up, then the horizontal stabilizers will actually act and return the aircraft to a resting angle of attack. They're also able to be utilized by the pilot in order to control the pitch of the aircraft. Helps the aircraft ascend and descend, especially useful during both ascent and descent. Horizontal stabilizers are used in a variety of applications in both commercial and military applications. Here on the screen you can see two diagrams of the horizontal stabilizers creating a pitching moment about the center of gravity of the aircraft. Stabilizers are also utilized in helicopter applications, although they don't have as large of an effect on the aerodynamics as they do in airplanes and other aircraft. Stabilizers exist in a variety of configurations. Here on the screen, as a lot of you recognize from last C term aircraft design, this is from our book. It shows a variety of configurations: the classic T-tail, the conventional vertical with two horizontal stabilizers, as well as a variety of others. If you notice, not all the configurations even have horizontal stabilizers. The V-tail, for instance, has no combines the vertical and the horizontal stabilizers, as well as the Y-tail and a variety of others. Typically, horizontal stabilizers exist in three configurations. The first configuration is a fixed horizontal stabilizer, where the main body of the horizontal stabilizer is fixed to the airplane. It cannot move at all, and in order to adjust the moment that the stabilizer produces, differences in the elevator is moved up and down in order to create different coefficients of lift and such. The second configuration is the all-adjustable configuration, where not only do the elevators move, but the horizontal stabilizer that was previously fixed can also be adjusted with its angle of attack with respect to the airplane. This is obviously a much more complex system and is generally used in commercial aviation, where advanced computers are controlling the aircraft on a more regular basis. A third configuration is known as the all-moving configuration, where the elevators are no longer independent of the horizontal stabilizer, but instead the entire horizontal stabilizer acts as the elevator itself. This is generally used in military applications, and these are generally called stabilators, as can be seen in the previous diagram. On the screen now is a table of various aircraft, from personal aircraft to large commercial aircraft to military. And as you can see, they all use different configuration for the horizontal tail. For this project, I decided to focus on the fixed wing configuration. As you can see on the slide right now, typical operating conditions of an airplane. Generally, airplanes, the lifetime of an airplane is about 50,000 flight hours, or about 75,000 pressurization cycles. And they generally operate in a temperature range between 15 degrees Celsius and negative 44 degrees Celsius. Typical failure of a horizontal stabilizer in these conditions would be due to corrosion or fatigue. On the screen you can see a diagram of a horizontal stabilizer. The two main components I wanted to highlight are the supporting ribs as well as the outer skin. The supporting ribs of the horizontal stabilizer are typically made out of either steel or titanium. Generally, steel is placed further inwards on the wing where it connects to the root of the aircraft and the actual body, whereas titanium is spread throughout the wing to give its stability. This generally supports an outer skin layer, um, which is typically made out of a polymer matrix composite. A variety of titanium materials can really be used for the structure of an aircraft. I found that the titanium 4 aluminum 4 molybdenum 4 tin and 0.5 silicon is one of the up and coming structural titanium alloys used within the industry. It typically has the important properties of having low density, a very high strength at room temperature compared to a lot of the other titanium alloys, as well as a high fracture toughness in order to withstand fatigue. As you can see on the screen, this titanium alloy has a density of between 4.4 and 4.8 times 10 to the third kilograms per meter cubed. It has a high strength of 1330 megapascals and a high fracture toughness of between 30 and 40 megapascals per square root meter. This titanium alloy is generally forged and is also solution heat treated and aged in order to increase the strength. The skin of an aircraft, as mentioned before, is generally made up of a polymer matrix composite. I found that the carbon fiber reinforced polymer is a very common fiber matrix that's used in aerospace applications. It has very good low temperature strength. It has a high strength to weight ratio, as well as good corrosion resistance. The fibers of the polymer matrix composite is generally made up of carbon filaments. These are generally made using polymers such as polyacrylonitrile, otherwise known as PAN, as well as rayon or petroleum pitch. They are usually taken and spun into filament yards where they are chemically and mechanically treated in order to align all the polymers. They're then spun into yarns where they are able to be heat treated so that only the carbon atoms remain. This is known as a process called carbonization, where they're then able to be stored and further heat treated in unidirectional sheets that are able to be used in the composite. The typical matrix that is used in these composites are epoxy resins. The polymer matrix composites are generally processed using single-piece molding, where the carbon fiber sheets are laid out within a mold, spanning the entire horizontal stabilizer. They're then filled with the epoxy resin, and then vacuum bagged and autoclaved in order to preserve the qualities of the epoxy and make sure that there are no bubbles form due to outside gases interacting with the treatment. The properties of the carbon reinforced polymers really vary from composite to composite. It depends on what you use for the fiber and the matrix that really have a huge influence on the final properties. Anyways, that concludes my presentation for the day. I would like to thank you for your time in watching the presentation and hope you all have a wonderful summer. Thank you.